So, good morning, everyone. Welcome you all to the third session on water treatment and water supply. So, to start about the water treatment processes, so in the last class we have known about what are unit operations and unit processes. So, we will going to start with the water treatment about the aeration. So aeration is one of the important unit operation where the gas transfer will takes place, and this is very much necessary to promote the exchange of the gases between the atmosphere and water. Okay, so the important objectives that the purpose for which we need to do the aeration is to remove the taste and odor, to increase the DO content, to remove the hydrogen sulfide, and to decrease the carbon dioxide content, and to convert the iron and manganese to the soluble from the soluble state to the insoluble state, and also to mix the chemical with the water. So this is the schematic representation which tells about the gas exchange, so which is going to obey the Henry's law. So this is depending on the saturation value of the water, that is the DO saturation value of the water. If the water has higher concentration when compared to the gas, so there may be chance that the gas resorption takes place from the bulk liquid. The oxygen will get transferred to the air or the gas, whereas in case the saturation value is lesser than the in the water is lesser than the gas or the air, then the oxygen from the gas will going to absorb in the water. So the important factor that affect the exchange of the gases is, one is the area of the interface, then the thickness of the interlayers, time of contact, partial pressure of the gas, degree of undersaturation or the oversaturation of gas in the water. And to ensure the proper aeration, we need to increase the area of water in contact with the air, and to keep the surface of the liquid constantly agitated to reduce the thickness of the liquid film. And the third important thing that we need to do to have a proper aeration is to increase the time of contact of water with the air. So the classification of the aerators mechanism, there are two mechanisms on which most of these aerators work. One is those forming drops or thin film sheets of water exposed to atmosphere. That is one mechanism. The another one is those forming small bubbles of air which rise in the water. So the types of the aerator that we use in the water and the wastewater treatments are these: gravity aerator, spray, mechanical, and the diffuse aerator. So in the gravity aerator, the important example or the important type of the aerator that is used is the cascade aerator. So the design criteria for the cascade aerators: number of steps 4 to 6, head requirement is about zero point 0.5 to 3 meter. The space requirement for the aerator is 0.015 to 0.045 meter square per meter cube hour. And then, sorry, gas removal efficiency, carbon dioxide is 20 to 45%, and hydrogen sulfide is about 35%. And another type of the aerator that is used is multiple tray aerator. So in this multiple tray aerator, the size of the coke or the ceramic that we are using in the trays will vary from 50 to 150 mm, and the number of trays spacing is about 4 to 9 trays with the spacing of the 300 to 750, and the height 1 to 3 meters, and the space requirement is 0.013 to 0.042, that is the area requirement per meter cube per hour of water. And the gas removal efficiency is 65 to 90 for carbon dioxide removal, and 60 to 70% for hydrogen sulfide removal. Okay, this is the spray aerator, so which are used in the water treatment and wastewater treatment. So the nozzle diameter in this will vary from 10 to 40 mm, and these are spaced at an interval of 5 to 1 meter. The pressure head at the nozzle is about 7 meter, and in practice, but it can vary from 2 to 9 meter. So the discharge rate per nozzle, according to the literatures, is 18 to 36 meter cube per hour, and the aerator area is can vary from 0.03 to 0.09. The gas removal efficiency for the carbon dioxide is maximum about 90% removal, whereas hydrogen sulfide is about 99%, okay, 90 to 99%. So this is the relation which we can able to use to calculate what is the time of exposure of that droplet. So depending on the whatever the angle of that nozzle and the head of the water, so we can calculate. Okay, so CV is refers to the coefficient of velocity, and X is the angle of inclination of the nozzle. H is the head of total head of water at the nozzle. Next is the diffused aeration system, or we call as diffused aerator. Next, the another type is the mechanical aerator, which is most commonly used in the wastewater treatment. So advantages of using this aeration is we can remove the iron and manganese. Okay, so these are the advantages that we can able to find with respect to removal of the iron and manganese. So similarly, we can able to remove not only iron and manganese, we can remove the hydrogen sulfide, and this is how the reaction takes place when we do the aeration. So hydrogen sulfide will react with the oxygen to form the water, and the elemental sulfur will going to released. So this aeration is the most effective treatment when we have a hydrogen sulfide at a lower concentration. If it is in a higher concentration, then we need to go for some chemical treatment. Okay, only at lower concentration, this aeration system is found to be beneficial. Next, coming to the limitation of the aeration, the unit operation of aeration requires the significant head of water, and because of the oxygen addition, the water will become more corrosive. Okay, and then the removal of taste and odor. Most of the time, this aeration has not proved to be a good treatment method, and then the additional lime may be required to neutralize the carbon dioxide that would be removed by the aeration. Okay, so these are the limitations that we can able to observe with respect to the aeration treatment. Next treatment is the sedimentation. As you know that sedimentation is the process of removal of the suspended particles through the gravitational settling. We can have the two types of sedimentation. One is plain, another one is sedimentation with the coagulation. Okay, these are the types of settling. Four types of settling can be observed with respect to the suspended particles. So we classify that as discrete, flocculent, hindered, and the compression. And as we remember that the sedimentation process is based on the Stokes law. Okay, and as the Stokes mm, proposed that depending on the diameter of the particle, the sedimentation process will going to vary. So the settling velocity of this particles is mainly dependent on the relation, and he has proposed the relation for the various diameters of the particle. For diameter having less than 0.1 mm, the relation is Vs equals to G into Gs minus 1 divided by 18V into D square, where Gs refers to the specific gravity of the solids, V is the viscosity. Okay, this is how the various settlings will be. The discrete, which is at the discrete settling, will be at the topmost part of that column, water column. Next is the flocculent, and next is the hindered, and the last one near the sludge zone is the compression. And we have the important features of these particular settling are: first one that we call as the type 1 settling. Settling of the discrete particles in the dilute suspension takes place, and the in here in this particular zone the particles will not have the tendency to flocculate. They will going to settle as the individual entity. Okay, that's why those particles which will going to remain as the individual entity, we call that as the discrete particle. So here we, that's why that particular settling we call as the discrete settling. Next, coming to the type 2, the settling of the flocculent particle in the dilute suspension will happen here. And as the particles settle, they will going to coalesce, means they get attached each other. And the sizes of the particles and the settling velocity will going to increase. A bit increase can be observed in this second type of settling. Third type of settling, that is the hindered settling, the settling of the intermediate concentration of the flocculent particle. So they are so close to each other, the interparticle forces are able to hold them in a fixed position. Like in the form of a film, they will going to move down in the water column, and it will be moving at a constant velocity. And the last one is the type 4, which we call as the compression settling. Here in this zone, the settling of the particle are such that the high concentration of the particle, which are very very thicker in nature, and they will going to settle by the compression of the particle which is just above it. Okay, so that type of settling, it is referred as compression settling. So coming to the types of sedimentation tank, so fill and draw type is one type of sedimentation tank, which is also called as quiescent or the intermediate type of sedimentation. And the second type is the continuous type of sedimentation tank. Okay, so this is the schematic representation of fill and draw type, where at the through the inlet the water will enter the sedimentation tank, and it will be retained for some particular time of duration, and after the end of that time the water will be taken out through the outlet. Okay, so that type, where certain quantity of water will be considered while providing the treatment, so that type of sedimentation we call as fill and draw type or intermittent. This is the continuous schematic of continuous sedimentation tank. So water will be allowing into the inlet zone. Okay, this is the inlet zone through the inlet pipe. And to reduce the velocity, or to have a constant velocity within the settling zones of the sedimentation tank, the baffle valves are used here. So the inlet zone, a baffle valve will be provided, which will going to reduce the velocity of the incoming water, and then the water will be going to flow in the direction as it is shown here slowly. And at the outlet zone, the water will be taken at the top of the tank, so that the supernatant water which is free from the flocks is taken to the next treatment unit. Design aspects that we need to consider for the sedimentation tank is, these are the important design aspects: velocity, capacity of the tank, and then the inlet outlet arrangement, shape of the tank, and the miscellaneous consideration. So when we are talking about the capacity, so capacity is mainly determined by, depending on the either the detention period or depending on the overflow rate. Okay, detention period is the theoretical time taken by the particle of water to pass between the entry and exit of the settling tank. Okay, so here the capacity of the tank, we can able to calculate using the relation q into t, where q we call as the rate of flow per hour, whereas t is the detention time period that we are allowing that particle to retain in the tank in the hours. Next is overflow rate. It is the quantity of water passing per unit hour per unit area of the settling tank. In common, we refer that as the surface overflow rate. Okay. So here we know that the sediment detention time in sedimentation tank, detention time is equal to capacity of the tank divided by the flow rate. Okay, so capacity is nothing but product of the length, breadth, and the depth of the tank divided by the discharge rate or the flow rate, that is q. Okay, this is one relation. So with that we can able to know what is the detention period. Another relation that we can able to have for the detention period is it is the settling of the particle that takes place. So time taken by the particles to settle, we can calculate using the relation distance of the descent of the particle divided by the velocity of descent. Okay, so the distance of the descent is nothing but the depth of the tank, and the velocity of the descent is represented as v. So it is d by v, so which we can also write as d by v equals to swd, that is side water depth, by the surface overflow rate. Okay, this is another relation which we can able to have to calculate the detention period. So when we equate equation 1 and 2, so we can simplify the relation for the surface overflow rate. So we got the surface overflow rate will be equal to flow rate divided by the area of the tank, that is L into B, surface area. Okay, so this shows that this particular relation shows that this sedimentation process or the sedimentation of the particle is not dependent on the depth. Okay, it is independent of depth. And depending on the type of the sedimentation tank, so we can have the various overflow surface overflow rates. So if it is plain sedimentation, if we want to consider the criteria overflow rate, then we can consider 40 to 50 meter cube per meter square hour, whereas in case of sedimentation and coagulation it is 50 to 60 meter cube per meter square hour. The shapes of the tank that we are using is rectangular, circular, and then the hopper bottom. Okay, so hopper bottom tank with the vertical flow. So in these three, the most commonly used is the circular tank with the radial flow is most commonly used. Okay, let me take an example on this sedimentation. Consider a primary sedimentation tank in the water treatment plant with the surface overflow rate of 40 meter cube per meter square day. The diameter of the spherical particle, which will have 90% theoretical removal efficiency in this tank, is dash micrometer. So we need to calculate the diameter of the particle and assume that the settling velocity of the particle in the water is described by the Stokes law, where they have given the property of that water, the density of the water particle, and then the acceleration due to gravity, viscosity of the water. So they have given the options. Okay, what is the diameter that will be removed based on these data? So answer is B, that is 22.58. Okay, so let us know how we got. So here the percent removal is Vs dash by Vs into 100. Okay, so where Vs dash we can take as 0.9 of the Vs, because here they have given that the diameter of the spherical particle, which will have 90% theoretical removal efficiency they have given. So based on this, we are taking that as 0.9. So Vs is 40. So since they have given in meter cube per meter square day, we need to convert that to second. So that's why we are dividing that by 86,400. And then once we got this Vs dash, then we can use this relation, the Stokes law. 1 by 18 into d square equals to g by mu into rho s minus rho w, that will be equal to the Vs. Okay, so we need to calculate the diameter of that particle. We don't know this value, so it is square root of zero point 0.9 into 40 into 18, okay, into V into rho W, then divided by 86,480 into GS minus 1 into rho W into G. Okay, when we simplify this, we will get the value of the diameter as 22.58. Okay, this is the most important question, I can say, because most of the time or in the previous year papers, these type of problems were asked in the uh, from the sedimentation tank. Next example is a water supply board is responsible for treating 1500 meter cube of water. A settling column analysis indicates that an overflow rate of 20 meter per day will produce satisfactory removal for a depth of about 3.1 meter, and it is decided to have two circular settling tanks in parallel. The required diameter of the settling tank should be how much they are asking, so which should be expressed in meters. So they have given the four options. So answer for this is C, that is 6.91. The procedure is, we know that the total area of the settling tank we can calculate based on the flow rate by the whatever the velocity. So here flow rate is given 1500 and the velocity is given as 20 meter per day. So here also it is meter per day. So when we divide this, we get the area as 75 meters square. And then they have given that the two circular tanks which are in parallel has to be provided. So the number of tanks that we need to provide is 2. So the area of the each tank will be obviously 75 by 2. So we get the area of each tank as 37.5 meters square. Now we need to calculate the area diameter of the sedimentation tank. So we know that area is known. So we need to calculate the diameter. So pi d square by 4. So for that, based on that, we will be calculating. So when we calculate, we get the diameter as 6.91. Okay. Next. Okay, here in the sedimentation tank, to increase the efficiency of the sedimentation tank or to reduce the detention time in the sedimentation tank, so another technique has been adopted is providing the tube settlers or the laminar plates in the sedimentation tank. So in this, what happens? The water which flows up through the slanted tubes, you can see. So this is the laminar plate and this is the tube module, so which will be placed in the sedimentation tank, as you can see here. As it is placed in the slanted position, as the water going to flow up through these slanted tubes or the plates, the flocks which are present in that water will get settled over these plates. Okay, so then since it is in a slanting position, that flocks, once the whatever the concentration of the flux that gets settles increases, that will going to slide down the tank and it will going to settle in the bottom of that tank. Okay, only the clear or the clarified water will going to passes through the tubes and it will going to come up from there. It will be next connected to the outlet channel. So in generally, the whatever the constituents that are provided in the coagulation sedimentation tank are these: feeding devices, mixing device, then flocculation tank, then the sedimentation tank. So, coagulants are the chemical that are used to destabilize the colloidal particles. So, the process of adding coagulant we call as the coagulation. So, where the destabilization of colloidal and the fine particles takes place and the initial aggregation of the destabilization of the particles happens. So the common coagulant that are used are aluminum sulfate, that is common name is alum, and then chlorinated copper as, then the ferrous sulfate, lime, magnesium carbonate, and the sodium aluminate. So the principle of the coagulation, there are two important processes that takes place in this coagulation. One is flock formation, the other one is the electric charge neutralization. Okay, so here flock formation means when we add the coagulant, that is, for example, I say alum, the alum will going to react with the water to form the aluminium hydroxide, which is a precipitate, insoluble precipitate. So those insoluble precipitates we call as the flock. So once the flock is formed, as we have known that the colloids are negatively charged particles, so the flock, aluminum hydroxide flock will going to attract this negatively charged colloidal particle, so that negativity of that colloidal particle will get neutralized. So that we call as the charge neutralization. Okay, so destabilization of colloidal particles takes place, so which is based on this double layer theory, we call as the double layer theory. So as you can see here, initially the coagulant, when we add, we will going to get the flux. So due to the whatever we call as the neutralization, the colloidal particles will going to get attached to the aluminum hydroxide flock, and neutralization takes place. Then the bridging will going to happen between the particle and the flock, and then it will get entrapped, colloids will get entrapped within that flock. Okay, and then we need to see that the whatever the flocks that are formed initially will be very small in size, so it has to grow to a bigger size so that it can settle on its own. Okay, so that process we call as the flocculation. So before we move on to the flocculation, uh, as you know that this is the jar test apparatus which we will be using to determine the optimum dosage of the coagulant. So let us know one example here, which is asked in one of the previous paper. A surface water treatment plant operates round the clock with the flow rate of 35 meter cube per minute. The water temperature is 15 degree, and the jar test indicated that the alum dosage required is 25 milligram per liter, with the flocculation at a GT value of 4 into 10 to the power of 4, which produces the optimum results. So we need to calculate the alum quantity required for 30 days. Okay, so these are the options. So answer is C. Okay, how we got? So let us know about it. The flow rate is 35 meter cube per minute, and then the dosage is 25 milligram per liter. So alum required for 30 days, we will multiply the whatever the flow rate into the quantity of alum dose that is required, which is in terms of milligram. So we need to express in terms of kg. So that's why we have multiplied here 10 to the power of minus 6. And since the we required for 30 days, not just for one day, because the flow rate and alum dosage they have given is depending on the quantity of water, and this is the water required per day. So we will be calculating per day if we multiply these two. Since we need the monthly requirement, so we are multiplying by 30. So we will get the answer as 37,800 kgs. So the coagulants are fed either in the dry form or in the wet form. Okay, these are the toothed mechanism and the helical screw or the methods that are adopted if we want to go for dry feeding. And these are the, that is conical plug and float, and the adjustable wear and float are the two methods that we can able to adopt if we want to go for the wet feeding. So coming to the mixing devices, so whatever the coagulant that is added should be mixed properly with the water. So we can either use the compressed air, or we can provide the hydraulic jump, or we can use the hydraulic jump method, or we can use the mixing channels where the baffle walls in the sideways will be provided in a, or then the mixing basins with the horizontal with the baffle walls in the horizontal directions. So, and also the mixing basin with some mechanical stirrers can also be used. Okay, okay, this is uh, mixing basin where the baffle walls are provided, and this is where the mechanical stirrer is used, okay, which is we call as the flash mixer. And flocculator, gentle agitation to aggregate the destabilized particles to form a rapidly settling flock, so that that is nothing but by increasing the size of the flock, we can make that flock to rapidly settling flock. That process we call as the flocculation. So the power required for this flocculator we can calculate using the relation P equals to half CD into rho into AP into VR, and also G is the square root of P by mu into V, where CD we call as the drag coefficient of the drag of the paddle, and VR is the relative velocity of paddle, AP is the area of the paddle, G is the mean velocity gradient, and V stands for the volume, flocculator volume, and mu is the absolute viscosity. Okay, so while designing the flocculator, these are the design criterias we need to keep in mind. The depth of the tank 3 to 4.5 meters, detention time 10 to 40 minutes, velocity of flow is zero point 0.2 to zero point 0.8 meter per second, area of the paddles is about 10 to 25% of the cross sectional area of the tank, and then peripheral velocity is zero point 0.2 to zero point 0.6 meter per second, velocity gradient is 10 to 75 per second, and GT factor for this flocculator will going to vary from 10 to the power of 4 to 10 to the power of 5, and the power consumption that is observed will vary between 10 to 36 kilowatt per mld of water that is treated. Outlet velocity 0.15 to 0.25, CD is 0.18 for flat blades, distance between the paddle edge and the side of the basin is 15 to 40 centimeter, and the K value is 0.25. Relative velocity is 75% of the paddle velocity, and the area of the paddles we can calculate based on the length of the blade, width, and the number of the blades that we have provided in that compartment. And the distance between the two paddles in the same compartment is about 1 meter. So if we take one example from the previous year paper, okay, this is one of the most frequently asked. A flocculation tank contains about 1,800 meter cube of water, which is mixed using the paddles at an average velocity gradient G of 100 per second. The water temperature and the corresponding dynamic viscosity are 30 degrees centigrade and 0.798 into 10 to the power minus 3 Newton per second per meter square respectively. The theoretical power required to achieve the stated value of the G we need to calculate. Okay, so here power required we can calculate using the relation. So all are given, we need to substitute that value. Okay, we will get the value as 14.36 kilowatts. So coming to the next treatment process, that is filtration. Uh, so the process of passing the water through the bed of sand or such granular material we call as the filtration process. So two types of filters commonly used for treating the water supplies. One is the slow sand filter, the other one is the rapid sand filter. So third type is also used, which is referred as the pressure filter, most commonly used for the to treat the water in the swimming pools. Okay, that is pressure filter. So whatever may be the type of filter, the mechanism will going to remain same. Okay, mechanism, or which we also call as the theory of filtration. So these are the four steps that takes place during the filtration process. One is the mechanical straining, flocculation and the sedimentation, biological metabolism, and electrolytic changes. Okay. So mechanical straining, depending on the size of the particle, the larger particles are get retained or get strained at the top surface. So that is called as mechanical straining. Then as the water passes through these voids, so it will, whatever the particle that will be passing through this voids, so will going to retain for some time, which will going to act as the chance for the flocculation, and also there may be chance of the sedimentation happens here. Okay, and then The microbes which get settled over these filter media will also going to absorb, or it will going to take the organic matter that is present in that water, and it will going to destabilize those organic matter, so where the biological action will also going to takes place during this filtration process, that is referred as biological metabolism. Okay, and along with this, to remove the fine flocks from this water, there is electrolytic changes takes place. Okay, because the sand is, as the water passes through the sand particles, there will be charge neutralization takes place here, so which will going to make that flocks to settle over this sand media. Okay, this is how the flocculation and the sedimentation happens within the voids. So to know about the filter media, as you know that most of the time we use sand as the filter media, commonly used filter material. The sand should be free from the dirt, should be uniform in nature and size, should be hard and resistant, and it should be such that not to lose more than 5% of its weight when it is placed in the when acid test is done for that sample. And the gravel which is used for the filtration process, its density should be about 1600 kg per meter cube. And other than the gravel, we can use the anthrafilt or anthracite as a filtering material, so that which will help us in removing the color from the water. If it is necessary, then it will be adopted. Next, types of the filters. We can have the various types based on the two factor. One is rate of filtration. The other one is based on the gravity or the pressure with which water is passed through the filter bed. So based on rate of filtration, we can have three types: slow sand filter, rapid sand filter, and the pressure filter. So as you move down, the rate of filtration will goes on increases. Whereas under the gravity or pressure filter, so gravity filter, the most important examples are which is passing water will be to pass through the gravitational flow, so that is slow sand filter and rapid sand filter. Whereas in pressure filter, water will be pressurized through the filter media. Okay, that's why it is called as the pressure filter. So this is how the slow sand filter is constructed. Okay, there is a inlet chamber here, and in the slow sand filter, the filter bed will consist of the sand media, again followed by the gravel, which is that gravel is placed above the under drains. Okay, and the whatever the water that passes through this filter media through the under drains will get collected in the outlet chamber. So where in the outlet chamber they will be having the circular float. Okay, so depending on the whatever the quantity of water that is collected here through this circular weir float, the water will be taken out of this outlet chamber. So these are the important components of this slow sand filter: enclosure tank, filter media. Okay, here the effective size of the sand that we are using in the slow sand filter is about zero point 0.2 to zero point 0.4 mm. Okay, please keep that in mind. Then the uniformity coefficient of the sand is 1.8 or to 2.5 to 3, and the okay, here the finer the sand, the efficiency will be higher. So then the other material is the base material. Okay, and the graded layers 150 each will be provided, and the size of these will going to vary from 300 to 700 depth. And also along with this base material, there will be under drainage system, inlet outlet arrangement, and the other apprentices like weirs, other gate valves, so which will be able to control the flow or the process rate of filtrations in that tank. Next, coming to the type of the filter media, okay, this is a table which tells about the type of the sand or the size of the sand or the gravel that is used in the various layers. So this is how the plan of the under drainage system in the slow sand filter. So it should be noted that the water entering the slow sand filter should not be treated by the coagulant, and the filter head is limited to maximum of about zero point 0.7 to 1.2. So cleaning of the slow sand filter is not done by backwashing. That is one of the important difference. We have to keep that in mind. Only the top layer will be scraped out and that will be removed. So about 1.5 to 3 centimeter of the top sand layer will be taken out. So whatever the biological film that will be formed over the surface of that filter bed, we call that as Schmidt's decay, okay, which is referred as the dirty skin. Okay, the slow sand filter rate of filtration is very less. Okay, it is about 100 to 200 liter per hour per meter square. So when the quantity of the water that we need to treat is less, so there they can adopt this slow sand filter, but the efficiency is very high. Bacterial removal efficiency is 98 to 99%. So this is the construction of the rapid sand filter, okay, where we have various components here. Mm, Inlet chamber, and then the filter bed, wash water troughs, then the compressor, then the wash water storage tank, under drains, okay, lateral drains, central drain, okay, and also the wash water drain. Okay, these are the various important component of this rapid sand filter. Okay, this is an isometric view how the rapid sand filter is constructed. So again, another isometric view. So enclosure tank, usually the depth will be 2.5 to 3.5 meters. Area will vary 10 to 80 meters square. And while calculating the number of units of filter bed that we need to provide, we will be using this moral and Wallace equation. Okay, based on the total quantity of water that we need to treat, we will be deciding how many number of filter units has to be provided. Okay, that is n equal to 1.22 into root q, where q will be substituted in mlds. So this is the size of the sand that we are using. So sand layer depth will vary 60 to 90 centimeters. Effective size 0.3 to 35 to 0.55 mm. Uniformity coefficient 1.3 to 1.7. Okay, this is the details of the base material that is being used in the rapid sand filter, and the under drainage that is used in the rapid sand filter mainly to collect the filtered water uniformly, and then to provide the uniform distribution of backwash water. So for that purpose we need to have a under drainage system. Okay, this is the section of the under drainage that is shown here. So these are the lateral drain and this is the central drain. So other apprentices which are needed in this rapid sand filter is wash water trough, air compressor, and the flow control devices. Okay, the operation of this rapid sander is simple here. From the inlet chamber, the water will be made to flow through the sand media, and in the under drainage system, the filtered water will be collected and it will be taken to the next treatment unit. But here, while cleaning the filter, we need to take the special care. A separate mechanism is observed for that. But the problem that is most commonly observed or faced in this rapid sand filter is air binding. So to remove or to overcome that problem of air binding, we need to avoiding development of the excessive negative head. So the loss of head should be restricted to about 2.5 to 3.5 meter, and negative head maximum about 1.2. And we need to control the growth of the algae and by remedying the condition that supersaturate the water with the air has to be done, and by taking the precautions if possible against water getting warmed as it passes through the treatment plant has to be taken care. Next, coming to the backwashing, okay, this is again the one of the important feature of this rapid sand filter. Because of this feature only, the rapid sand filter is most commonly used in the conventional water treatment plant. Okay, we can, instead of taking out the top sand, we can clean the sand bed with the help of the water by allowing it into flow in a reverse direction. So, rapid sand filter are washed by sending air and water upwards through the bed by reverse flow. And here, 2 to 4% of the filtered water that is we are treating will be used for backwashing. So here the mechanism is from the we will going to open the valve here, the back wash water valve, and the outlet pipe will be closed. So from the backwash water tank, we will allow the water to the under drain. So from the under drain, the water will going to move up. Not only water, even the air will be passed through this sand bed, so that it loosens the whatever the compacted sand particles, and then the water will be made to flow this. And in the wash water troughs, okay, these are the wash water troughs which are placed above the sand bed. So in this wash water trough, the water will be collected, and then again that will be connected to the outlet wash water outlet chamber or the drain. So here the air that we blow should be at a rate of 1 to 1.5 meter cube of air per minute per meter square, and for about 2 to 3 minutes we need to blow. To take a problem on this, the water treatment plant of capacity 1 meter cube per second has filter box of dimension 6 meter by 10 meter. The loading rate to the filter is about 120 meter cube per day meter square. Okay, so when two of the filters are out of service for backwashing, the loading rate we need to calculate. Okay, they have given the options. So let us know how we arrived at this 144. The total quantity of water filtration per day we need to calculate here. So 24 into 3600 into 1, that is 1 meter cube per second they have given. So we need to convert that to meter cube per day. So that's why we are multiplying this. So we get 86,400 meter cube per day. So surface area we can calculate based on the surface overflow loading rate they have given here. Surface overflow rate is given. So area quantity of water divided by the SOR will give us the surface area of the tank. Then area of the one filter unit, they have given the dimension. It is 60, 6 into 10, 60 meters square. If one filter unit has an area of 60 meters square, to have a total area of 720 meters square, how many number of filter beds we need to provide? So that is totally 12 number of filter units we need to provide, and 2 will be out of service or kept as a standby, and only the 10 filters will be operated to treat the whatever the required quantity of water. Okay, so surface area of the filter totally 600 meters square. So the quantity of water they are treating will be 86,400 meter cube per day divided by the surface area of the filter 600. So we get the loading rate as 144 meter cube per meter square per day. Okay, that is the loading rate. So similarly, another problem, a rapid sand filter comprising a number of filter bed is required to produce 99 mld of potable water. Considering the water loss during the backwashing is 5%, the rate of filtration as 6 meter per hour, and the length to width ratio of the filter bed is 1.35. The width of the each bed is kept equal to 5.2 meter, and one additional filter bed is to be provided to take care of the breakdown or the repair. What is the total number of filters that is required? We need to calculate. Okay, so here water to be filtered is 99 into 1.05 mld, because they have given that water loss during the backwashing is 5%. So while calculating the total water that we are treating, we need to consider that. So that's why we have multiplied as 1.05. So total quantity of water that we are filtering is 103.9995 mld. So then the length to width ratio should be as per the given data at 1.35, where the breadth is 5.2 meters they have given. So then we can say the length will be 7.02 meters. So the area, surface area of the each filter bed is 5.2 into 7.02. So we get around 36.504 meters square. So the total surface area required will be discharged to the filter by rate of filtration. So we will get as 721.875 meters square. And the total number of working units required. So whatever the surface area divided by the 36 is the surface area of the each filter. So we get the number of filters. So it is about 20 filters. One unit is added as a standby. So totally 21 unit has to be provided. So this is the table which shows the comparison of rapid sand filter and the slow sand filter. Pressure filter, okay, as I told you earlier, a filter which is enclosed in a space and the water passes under pressure. So where the pressure of the water will be maintained about 300 to 700 kilonewton per meter square, which is greater than the atmospheric pressure. So these are the two configurations of the pressure filters, vertical and the horizontal, which are generally used in the swimming pools. Okay, wherever the space is less, they will go for the vertical orientation. If the space, enough space is there, then they will go for the horizontal. So these are the important constituents which are used in the construction. Closed cylinder, diameter 1.5 to 3 meters, length or the height 3.5 to 8 meter, and the manhole will be provided at the top for inspection. So working is water mixed with coagulant is directly admitted to the pressure filter, and in working condition all the valves are closed except the outlet valve. So cleaning will be through the compressed air to agitate the sand grains, and the valves that are used for wash water and the wash water drains are open during the washing. And the rate of filtration here is 6,000 to 15,000 liters per hour per meter square. Okay, less efficient than the rapid sand filter. Okay, the last treatment process is the disinfection. So it is the process of killing of harmful bacteria. The substance or the water that are used for disinfection are called the disinfectants. When water leaves the filter plant, it is still found to contain some impurities, especially the very, very small microorganisms like bacteria or some dissolved inorganic salts, color or taste, and even some extent of iron and manganese in the dissolved form. So for that purpose, we need to go for the disinfection. While selecting the disinfectant, we have to keep these points in our mind. Residual concentration should be obtained after the treatment, effective in killing all pathogenic organisms, should be harmless and economical, easy and available and unobjectionable in nature, and the strength can be easily determined of that disinfectant, and not much skilled personnel are required to add this disinfectant, and it should not need any costly equipment for the addition or to add, and it should take a reasonable time, small time for the to bring out the disinfection process. So these are the methods of disinfection. If we are using the physical agents, that is by heat or light, we can bring out the process of disinfection. Or when we are adding the chemicals, we can add the oxidizing chemicals, metal ions, alkalis, acids, and other surface active chemicals. So these are the minor method, that is the boiling, which is commonly used at the households level. And again, another one is the excessive lime treatment, which is used at the rural areas. Iodine and bromine treatment can be done to do the disinfection process, and even the silver treatment can be provided to bring out the disinfection process, and even the ozone treatment can be used to bring out the disinfection of water. So each method will have their own advantages and the disadvantages. So again, the water can be treated with the potassium permanganate to do the disinfection process, or treatment with the ultraviolet rays can be done. So what happens, whatever the nature of the disinfection method, this is the mechanism that happens. So the disinfectant will going to damage the cell wall, and then after damaging, it will be entering into the cell and changing the cell permeability, and then changing the colloidal nature of the cell protoplasm, and then it will going to inactivate the enzymes in that protoplasm, which are responsible to bring out the metabolic activity. Okay, so to talk about the disinfection kinetics, when a single unit of microorganism is exposed to a single unit of disinfectant, the reduction in the microorganism will going to follow a first order reaction, kinetic reaction, and mathematically it can be represented as n equal to n naught e to the power of minus kt. Okay, this equation we call as the Chick's law. The factors that affect the disinfection process are these: type, condition, concentration, and distribution of organism, type and concentration of the disinfectant, chemical and the physical characteristics of water, contact time available for disinfection, temperature of water. So, of all these, most commonly used disinfectant is chlorine, because it can provide it can be added easily, readily available, cheap, very toxic to most of the microorganism, and it is easy to apply due to the relatively low solubility. Okay, so this is the mechanism or the chemical reaction that takes place. So water reacts with the chlorine at a pH more than 5 and forms hydrochloric acid and hypochlorous acid. So this hypochlorous acid is unstable in nature. So when the pH more than 8, this hypochlorous acid will again dissociate to form hydrogen ion and hypochlorite ion. Okay, these are the chlorine, hypochlorous acid, and hypochlorite ion are the forms of chlorine which can going to affect or damage the cell wall of the microorganism. So these are the various forms of hypochlorites that are being used in the water treatments. These are some commercial names, and chloramines can also be used in the disinfection process. Chlorine dioxide is also used in the disinfection process, but most commonly used form of chlorine is the gas in the gaseous form, that is free chlorine gas, which will be stored in the cylinder under a pressure of about 700 kilonewton per meter square. So depending on how where we add the chlorine, we have the various types of chlorination: plain chlorine, pre-chlorine, post-chlorine, double chlorination, breakpoint chlorination, superchlorination, and dechlorination. And breakpoint chlorination is one type of chlorination that we most of the time we will be using in our laboratories to know the chlorine demand of the given water sample. Okay. The tests that we conduct to check whether the residual chlorine is there in the water are orthotolidine test or DPD test, that is diethyl paraphenylene diamine test, and then the chlorotex starch iodide test. So, to take one example on this, water purification works handles about 50,000 meter cube per day of water and consumes 20 kg per day of the chlorine. The residual chlorine after 15 minutes of contact time is zero point 0.2 milligram per liter. So, dash is the chlorine dosage used in the treatment. So, the answer is zero point 0.6. So let us know how we got. So here they have given, we need to calculate the chlorine demand. So they have given that whatever the quantity of water that is being treated and the consumption. So 20 kg we will be expressing in terms of milligrams. So multiplying 10 to the power of 6 divided by the quantity of water that we are treating. So we will get the chlorine demand as zero point 0.4 milligram per liter. That is the quantity of chlorine that is used in the process. But still, as zero point 0.2 milligram per liter is retained, so the chlorine dose, total chlorine dose that we have added is chlorine demand plus the residual chlorine is zero point 0.6. So another example on the E. coli. So here chlorine is used as the disinfectant. It achieves 50% of disinfection efficiency in terms of killing the E. coli in 3 minutes. So the minimum time required to achieve 99% efficiency, we need to calculate. Whatever the time of contact has to be calculated. So here we will be using the relation efficiency equals to N naught minus NT by N naught, and they have given that efficiency is 50%, so we are taking that as zero point 0.5. So when we, let us simplify that, when we we know that nt equals to n naught e to the power of minus kt, that is according to the Chick's law. We substitute that and simplify, so we can write, we simplify and write that as 1 minus e to the power of minus kt. Now, we, on further simplification, if we calculate the k value, that is 0.0, 0.231, 0.231 is the k value. And to achieve 99% removal efficiency, so what is the time period we will going to calculate based on this relation? And we, when we do the simplification, we get the t value as 19.93 minutes. Okay, that is the D is the correct answer. So another problem, wastewater to be disinfected with 35 milligram per liter of chlorine to obtain 99% kill of the microorganism. The number of microorganism remaining alive at time t is modeled by the Chick's law, where n naught at time t equals to 0 and k is the rate of kill. The wastewater flow rate is 36 meter cube per hour and the k value is given as 0.23 minute. If the depth and the width of the chlorination tank are 1.5 meter and 1 meter respectively, length of the tank we need to calculate. Okay, so here for 99% kill of the microorganism, using the relation we can write that as 0.99, and nt equals to 0.01 n naught. Let us further simplify that relation here, and we will be calculating the t value based on this. T value is 20.022 minute. So volume of the tank that is required will be Q into T. So we will be calculating the volume, and once we know the volume, we can calculate the length. Okay, because they have given the depth and the width of that chlorination tank, so we can calculate the length. So we got the answer as 8.0089. So, coming to the water distribution system, which is the last part of this session. So, the purpose of the water distribution is to deliver the water to consume the appropriate quality and quantity and with the required pressure. It is used to describe collectively the facilities used to supply the water from the source to the point of usage. The requirement of the water distribution system, it should not get deteriorated during the supplying. Water quality should not be affected. It should be capable of supplying water at all the intended places with sufficient pressure. It should be capable of supplying requisite amount of water during the firefighting. The layout should be such that no consumer would be without the water supply. In case of any repair, all distribution pipes should be preferably laid 1 meter away and above the sewer line, and it should be fairly watertight in nature. The methods of water distribution system will going to depend on these factors. Level of the source, excuse me, topography of the area, and other local conditions. So these are the gravity system that is system that is employed: gravity system, pumping system, combined gravity, and the pumping system. So it is suitable only when the source of supply is at sufficient height and most reliable and the economic distribution system. Okay, whereas pumping system, treated water is directly pumped into the distribution main without any storing, and high lift pumps are required in this case, not commonly generally used because it won't be economical. Most of the time we go for, other than the gravity, we will go for the combined gravity and the pumping. Okay, this is the most common system. Then supplies to the consumer by the action of the gravity. It will be initially pumped and stored in the elevated reservoirs, and then it is distributed. Layout of the distribution networks will be laid below the road pavements, and generally layout will going to follow the layout of the roads. There are different types of the pipe networks that are used: dead end system, radial system, gridiron system, and the ring system. So usually dead end system is suitable for the old towns or the cities. So it has its own advantage and disadvantage. Cheaper, and the discharge, determination of the discharge and pressure easier due to the less number of valves. But the disadvantage is there are many, due to the dead ends, the stagnation of the water may occur in the pipeline. Whereas in the radial system, the area is divided into different zones. The water will be pumped into the distribution reservoir, which is kept at the middle of that zone, and the supply pipes will be laid radially, ending towards the periphery. Okay, this is how the schematic representation of radial system. It gives quick service. Calculations of the pipe sizes will be very easier. So, in case of the gridiron system, it is suitable for cities which are developed with the rectangular layout, and where the water mains and the branches are laid in the rectangular shapes. Okay, this is how the schematic shows. You will going to have the main line at the center, and the all the sub mains are represented here on the lateral sides. Advantage: the water will be kept in good circulation condition, and in case of breakdown in some section, the water is available from the other direction. The disadvantages: exact calculations of the pipe sizes is difficult. And the another system is the ring system. The supply main is laid along all the peripheral roads, and the sub branches out from the mains. So this system also follows the gridiron system with the flow pattern similar to that of the dead end. The determination of the size of pipe is easy. Okay, this is the schematic representation of the ring system. So at the periphery, we will going to have the main lines, and in within the zone or the area, we will be having the sub mains. Advantage: so water can be supplied to any point from the least two directions. So distribution reservoirs, depending, we can say service reservoirs or the storage reservoirs, which will be helpful to meet the fluctuation demands. So functions of the distribution reservoirs to absorb the hourly variation to maintain the constant pressure, and water stored can be supplied during any emergencies like fire emergency. The location height of the distribution reservoirs should be located as close as possible to the center of the demand, and the water level in the reservoir must be sufficient elevation to permit the gravity flow at an adequate pressure. Okay, so this is one representation how the impound or the service reservoirs is. So types of the reservoirs, depending upon the elevation with respect to the ground, we can classify as surface reservoir and the elevated reservoirs. Surface reservoirs we also call as the ground reservoirs. Most of the time they are circular or rectangular in shapes. So ground reservoirs are preferably when the large size is provided. These reservoirs are constructed on high natural grounds. So side walls are designed to take up the pressure of the water, and the position of the groundwater table is also considered while designing these reservoirs. The floor of these reservoirs may be constructed with the RCC slabs. To obtain the water tightness, bituminous compound are used in all the construction joints, and the top of the roof, about 60 centimeter thick earth layer is deposited and maintain the green loss to protect the reservoir from the cold or to maintain the temperature within the reservoir, we can say. For aeration of water and the inspection, ventilation pipes and the stairs are provided. Okay, this is one schematic representation of the underground reservoir. Then coming to the elevated reservoirs, which we call as the elevated tanks. So RCC tanks is one type, which is most popular. They have long life, very little maintenance, and it is recent in appearance. Whereas GI tanks are generally rectangular or square in shape, not much preferred when compared with the RCC. GI is not preferred because of these reasons. HDPE is are being used presently, very popular for storing less quantity of water at the individual households level, and cleaning of the tanks are easy. So elevated storage reservoirs or the overhead tanks are required at the distribution areas, which are not governed or controlled by the gravity system of distribution. Rectangular, elliptical, circular shapes are preferred. Uh, they are constructed where combined gravity and pumping system of water distribution is adopted. These tanks may be steel or RCC. RCC is most preferred one. The accessories of the elevated service reservoirs are inlet outlet pipe, overflow pipe, discharge into the drain, the float gauge indicating the depth of water, then the automatic device to stop the pumping when the tank is full, then the a manhole and the ladder for in and out movement, and the ventilation for circulation of the free air, fresh air. Okay, so this is how the elevated reservoirs, storage reservoirs will be. To determine the capacity of this storage reservoir, so we need to take the summations of, one is the balancing storage. Okay, balancing storage means the quantity of water required to be stored in the reservoir for equalizing or balancing the fluctuating demand. Then the breakdown storage we need to consider, so which is often called as emergency storage. So it is the storage preserved in order to uh, meet the emergencies posed either due to the failure of the pumps or any electricity failure of the pumps, or maybe the electricity failure, they no electricity supply, or any other mechanisms when the pumps are driven. And a value of about 25% of the total storage capacity of the reservoir, or 1.2 to 1.5 to 2 times the average hourly supply may be considered as enough provision. So another type of storage we need to consider is the fire storage. This is the third component when we are calculating the total reservoir storage. This provision takes care of the requirement of water for extinguishing the fires. A provision of 1 to 4 liter per person per day is sufficient to meet the requirement. And when reservoir storage is elevated, reserve storage is elevated, the amount of fire reserve may be determined by using this relation R equal to F minus P into T, where R is reserve storage, F is fire demand, P is reserve fire pumping capacity, and T is the duration of the fire. So total reservoir storage can finally be worked out by adding all these three storage. So please keep that in mind while determining the total reservoir capacity. We need to add the balancing storage, then fire storage, and then the second one which we studied is the breakdown storage. Okay, so these are the three storages which are added to calculate the uh, storage capacity of the service reservoir. Okay, so with this I will close this session. Thank you for your patience listening.